A man in Shanghai put on a headset. Not a VR headset, not a gaming headset. A thin, lightweight band that wrapped around his forehead and sat against his scalp. No wires going into his skull. No surgery. No anesthesia. No recovery time. He sat in a chair at the 2026 World Artificial Intelligence Conference, looked at a robotic arm on a table in front of him, and focused on a specific mental pattern he'd been trained to produce, the kind of deliberate motor imagery that the system was designed to recognize. The arm moved. He shifted to another trained pattern. The gripper closed. Another pattern. The arm lifted. The audience watched a man operate a machine using the electrical signals inside his own brain, not by thinking freely, but by producing specific rehearsed mental states that an AI had learned to decode. And the delay between his mental command and the robot's response was less than 200 milliseconds, faster than a human blink. That happened in June 2026, and almost nobody outside of China talked about it. The company behind it is called BrainCo. They're a Chinese brain-computer interface company that has been working on neural technology for years. They were originally incubated at Harvard's Innovation Lab and have since built their primary operations in China. And what they demonstrated at the World AI Conference was not a single product. It was a platform. A system that connects a non-invasive EEG headset to an AI translation layer that converts brain signals into robot commands in real time. According to the company, any compatible robot, a robotic arm, a humanoid robot, a robot dog, a wheeled system, can be connected to the platform by a developer in roughly 10 minutes using their software tools. That's the claim. And if it works the way they say it does, it changes how we think about controlling machines. To understand why this matters, you need to understand the current landscape of brain-computer interfaces. Because when most people hear controlling things with your mind, they think of one company, Neuralink, Elon Musk's startup that implants a chip directly into the brain. Neuralink has dominated the BCI conversation for years, and for good reason. Their approach offers the highest signal quality currently possible. By placing electrodes directly into brain tissue, Neuralink can read individual neuron activity with extraordinary precision. Their early patients have demonstrated the ability to control computer cursors, play video games, and type text using only their thoughts. The results are real and impressive. But there is one requirement that Neuralink cannot get around: surgery. A neurosurgeon has to open the skull, implant a device into the brain, close the skull, and monitor the patient through recovery. It is a medical procedure. It carries the risks of any brain surgery: infection, bleeding, swelling, device rejection, scarring. And it is irreversible in the sense that once the device is implanted, removing it is another surgery with its own risks. For patients with severe paralysis or locked-in syndrome, people who have no other way to communicate or interact with the world, that trade-off makes sense. The benefits are enormous and the alternatives are zero. But for everyone else, the idea of elective brain surgery to control a robot is not realistic. Not today, probably not for decades. The vast majority of people who might want to interact with machines using their thoughts will never agree to have their skull open to do it. That's not fear. That's a reasonable assessment of risk versus benefit. And that's the gap BrainCo is trying to fill. Not by building a better brain implant, by avoiding the implant entirely. Their system uses electroencephalography, EEG. It's a technology that has existed since the 1920s. EEG works by placing electrodes on the surface of the scalp, not inside the brain, not through the skull, on top of it, and recording the electrical activity that passes through the skull and scalp from the neurons firing below. It's the same technology used in hospitals to diagnose epilepsy, monitor sleep disorders, and study brain function. It's completely non-invasive. You put the headset on. You take it off when you're done. No medical procedure. No recovery. No scarring. No risk of infection. You can do it at a conference and go to lunch afterward. The problem with EEG has always been signal quality. And this is where honesty matters. The human skull is a thick, dense barrier. It sits between the brain's electrical activity and the electrodes trying to read it. By the time a neural signal passes through brain tissue, cerebrospinal fluid, the skull itself, and then the scalp, it has been dramatically weakened and distorted. An EEG headset does not read individual neurons. It reads the blurred, averaged, noisy sum of millions of neurons firing simultaneously beneath a broad area of scalp. It's like trying to listen to one person's conversation in a stadium full of people by pressing your ear against the outside wall. You can tell something is happening inside. You can detect general patterns, excitement, quiet, rhythmic activity, but you can't make out the specific words. That's why invasive implants like Neuralinks produce dramatically better signal quality. They're inside the stadium. They can hear individual voices. EEG is outside the wall. It gets a muffled version of the whole crowd. So how did BrainCo take that muffled signal and use it to control a robot arm with enough precision that the audience at a major AI conference watched it work in real time? The answer, according to the company, is artificial intelligence. And to understand what the AI actually does, you need to understand what the brain produces when someone imagines moving their arm. When you think about moving your right hand, not actually moving it, just imagining the motion, specific regions of your motor cortex produce distinct electrical patterns. These patterns are different from when you imagine moving your left hand, or gripping, or releasing. They're faint, they're buried in noise, but they're consistent. If you imagine the same motion 20 times, the EEG pattern is recognizably similar each time. That consistency is what the AI exploits. BrainCo's system doesn't try to decode every neuron or read your inner thoughts. It doesn't know what you're thinking about for dinner. What it does is recognize trained motor imagery patterns, specific rehearsed mental states that the user learns to produce on command. Move left, move right, grip, release, lift, lower. The user trains with the system, producing each pattern repeatedly until the AI has enough data to distinguish one from another. Once trained, the AI recognizes those patterns in the live EEG stream and maps each one to a robot command. And it does that recognition in under 200 milliseconds. Think of it this way. The EEG headset is a bad microphone. It picks up a muddy, distorted version of what the brain is doing. But the AI is an incredibly sophisticated listener that has heard thousands of hours of that same muddy audio and has learned to pick out specific phrases despite the noise. The microphone didn't get better. The listener got smarter. That's a meaningful technical achievement. It doesn't match the precision of an invasive implant. It probably never will. The physics of signal degradation through the skull sets a hard ceiling on what non-invasive EEG can do. But for the task of sending categorical commands to a robot, move this direction, grip this object, perform this action, categorical precision may be enough. You don't need to read every neuron to tell a robot arm to go left. You need to reliably distinguish go left from go right, from grip from release. And if the AI can do that with 90+% accuracy in under 200 milliseconds, the user experience starts to feel responsive and intuitive. At the WAIC demonstration, BrainCo showed users controlling a robotic arm through a sequence of tasks. The arm responded to mental commands with visible speed and consistency. The company also showed the system connected to other robotic platforms, the kind of modularity that suggests the platform is designed as a universal translation layer between human thought and robotic action, not a custom solution for one specific device. According to BrainCo, a developer can connect a compatible robot to the platform in about 10 minutes using their software development kit. That claim was made during the conference presentation and has not been independently tested in third-party development environments. If it holds up under real-world conditions, the implication is significant. It would mean the brain-robot link is not locked to one proprietary robot. It would be an open interface. Any robot that speaks the platform's language could potentially be controlled through trained mental commands. That would turn brain-computer interface technology from a specialized medical device into a potential developer tool. But that transition, from conference demo to reliable developer platform, is a step that has not yet been publicly verified. But this is where we need to separate what was demonstrated from what is proven. The WAIC demo was a controlled environment. The lighting was set. The user was focused. The tasks were predefined. The robotic arm was performing relatively simple categorical movements, directional commands, and grip states. That is very different from operating a robot in a noisy factory, a chaotic warehouse, or a home environment where the user is distracted, tired, stressed, or multitasking. EEG signals are extremely sensitive to interference. Muscle movements, even clenching your jaw or moving your eyes, produce electrical signals that can overwhelm the brain's signals the headset is trying to read. Sweat on the scalp changes electrode conductivity. Environmental electrical noise from nearby equipment can corrupt the signal. In a quiet conference demo with a focused user, these problems are minimized. In the real world, they are constant. The world's first integrated brain-to-robot AI R&D platform claim is also worth examining carefully. BrainCo describes their system this way, but that claim has not been independently verified. Other companies and research institutions, including academic labs at MIT, Stanford, and Carnegie Mellon, have built EEG-to-robot control systems for research purposes. What BrainCo may be claiming as first is the specific combination of features: non-invasive EEG, AI translation, sub-200 millisecond latency, and multi-robot compatibility in a single integrated developer platform. That's a narrower claim than first brain-to-robot system. But the marketing language doesn't always make the distinction clear. The platform is also explicitly early stage. It is not a consumer product. It is not available for purchase. It is a research and development platform intended for developers and researchers. That means the distance between this demo and a product you could buy and use is measured in years, not months. And the history of brain-computer interface technology is full of impressive demos that never became functional products. The gap between a controlled demonstration and a reliable daily use tool is enormous in BCI technology, and many companies have fallen into that gap. There's also a broader question that goes beyond BrainCo specifically. If non-invasive brain-to-robot control eventually becomes reliable and affordable, and that is still an if, not a when, who gets access to it first? The most immediate application, and the one closest to current capability, is in healthcare. Researchers have already demonstrated EEG-based control of prosthetic limbs and wheelchairs in laboratory settings. Allowing paralyzed patients to control assistive robots without invasive surgery is a genuine and important use case that is actively being studied in clinical research around the world. That's not speculation. That's ongoing work. The next tier, further from today but actively being explored, is industrial. Operators controlling warehouse robots, manufacturing arms, or logistics systems through trained mental commands instead of joysticks and keyboards. Several companies and research groups are running pilot studies in this area, but no system is deployed commercially for industrial brain-to-robot control yet. And behind that, further still but impossible to ignore, is the military interest. Soldiers controlling drones, unmanned vehicles, or robotic systems through thought in combat environments. That application is not being demonstrated publicly, but it is almost certainly being researched privately. Every significant brain-computer interface technology in history has attracted defense interest. DARPA, the US Military's research agency, has funded BCI research for decades. China's military research apparatus has similar programs. The idea that this technology will remain purely commercial or purely medical is not realistic. The applications are too obvious and the strategic value is too high. That doesn't make the technology bad. It means the conversation about who controls it and how it's regulated needs to happen alongside the engineering, not after the products ship. But here's what BrainCo actually proved at that conference in Shanghai, stripped of the marketing and the speculation. They proved that a non-invasive headset reading surface-level brain signals through the skull can, with the help of AI, translate trained motor imagery patterns into robotic action fast enough that the experience feels responsive. They proved that you don't need brain surgery to make a robot respond to your mental commands. They proved that the bottleneck in non-invasive BCI was never the hardware. EEG headsets have been around for a century. The bottleneck was the intelligence interpreting the signal. And artificial intelligence has now reached a level where it can extract useful categorical commands from noisy, degraded, skull-filtered brain data in under 200 milliseconds. The headset didn't get better. The AI got smarter. And that shift matters more than any single demo. Because if the limiting factor was always the hardware, if you needed a better sensor, a thinner skull, a closer electrode, the path forward would be surgery. Invasive implants. Neuralink's approach. And for maximum precision, that path will always be superior. But if the limiting factor was the software, if the problem was never reading the signal but understanding it, then every improvement in AI makes non-invasive BCI more capable without anyone going under a knife. Every year, AI gets better at pattern recognition. Every year, it needs less data to make accurate predictions. Every year, the bad microphone, that is EEG, becomes more useful, not because the microphone improved, but because the listener learned to hear more clearly through the noise. BrainCo didn't solve brain-computer interfaces. They didn't replace Neuralink. They didn't build a consumer product. They built a research platform, showed it working at a conference, and made a case that the future of mind-controlled machines might not require a surgeon. A man in Shanghai put on a headset. He focused on a trained mental pattern. A robotic arm responded. No incision, no implant, no hospital stay, just a band on his forehead and an AI that had learned to recognize specific motor imagery through the skull. The signal was noisy. The skull was in the way. The AI heard through it anyway. And the robot did what he intended. The brain didn't need surgery to talk to a machine. It just needed someone to build a better translator.